on accelerate. So what is accelerate? And pardon for the cutting off on the presentation. Porto just decided to completely bug out on me in the last since the last time I edited this. I touched nothing, I swear. So accelerate is three libraries in one. So you have what I'll call a launching interface, you have a training library, and you have the big model inference. Now, basically, what this culminates to is launching interface is there's certain things that are required for you to do to, say, launch a Python script in a multi GPU scenario, a TPU scenario, or a single, a single node of, say, like a single GPU or a CPU. There's all these different commands that you need to do that, and so Accelerate provides a launching interface for you to do that very easily. The second is a training library, and similar to sort of the ideas behind the launching interface, the training library lets you use the exact same code that you've written out for your training loop, replace about 3 lines of code or so, and add one, no, two. And what Accelerate then lets you do is say, okay, given this training code, it is also, without any modifications, going to work on multi GPU, TPUs, TPU pods, CPU, and a single GPU. Because every single one of those different training paradigms requires a lot of custom wrappers to your model, different backwards pass calls, and all of them operate a little differently. And so Accelerate helps you solidify this very easily so that you don't have to worry about, oh, I got access to this TPU pod that I can go and try and play with, but I don't know how to train on TPUs. Just use Accelerate and it will train for you, essentially. And then the last one is big model inference. This one became very prevalent with the rise of stable diffusion. If you haven't heard of Accelerate's big model inference, I'd be very surprised, genuinely, because it is essentially what allowed stable diffusion to be ran on consumer hardware. And in general, big models ran on consumer hardware. I'm not going to cover big model inference really. The presentation I did for weights and biases covers that in depth. And it's inference, it's not training, which fastai is a training library. So we're going to focus on the launching interface and the training library. Now, let's talk about that a bit more. Why can't you just do Python do the thing, as I sort of alluded to a second ago? So these different commands, right, that each library uses needs a special interface, essentially, to tell its hardware, hey, I want to launch using this particular setup. So the first option, Python script.py, will only use a single GPU or a single CPU. The second command, torch run, you specify the number of computers, that's the number of nodes, and you specify the number of processes per node, or the number of GPUs per machine. And then you pass in the script you want to run and any arguments afterwards, and that will then run that script using 2 GPUs. All right, what if we get into, say, something like deep speed, which is by Microsoft that we're going to talk about a little later. Well, then you pass num GPUs equals 2, script.py, and there's many more beyond that. As you run with XLA, it has its own command to a certain extent. And so there's all these different commands that you have to remember. Each parameter is slightly differently. Deep speed calls it num GPUs, torch run calls it num procs per node, and there has to be a better way of doing this. And the answer is accelerate launch script.py. So with a single command, you basically are able to launch with deep speed, fully sharded data parallelism, those multi-CPU, multi-GPU, and TPUs. And the nice thing here as well, if you train on TPUs, for those of you familiar, generally you have to create this function called a map function, this underscore MP underscore FN. With Accelerate, it's able to actually just pick up your main function and work with it regardless, which helps in this idea of, hey, we're going to make sure every single thing in your script works on every single platform. Now, how does it do this, right? Because obviously it needs some way to know what GPU you're running, how many processes you're running, and so forth. Accelerate has essentially a configuration CLI to use, or command line interface, via accelerate config. And essentially, what this does, I believe there should be a GIF later of this, but essentially it gives you a bunch of questions asking you, how your process is set up. So, like, how many GPUs are you using? Are you using a TPU? Is there any device configurations you want to have? And it will save this away into a YAML file in Hugging Face's cache folder it makes. And so this is what enables you to do accelerate launch script, because it's going to read from this file and go, hey, all right, this is how he wants it. Let's go run it. Now, if you say don't want to do that, you don't want to go through a fairly extensive CLI interface and you just want to run, Accelerate lets you have practically one-to-one pass-ins for all of the different parameters for everything. Now, this should be num processes, not mprocs per node. I'll make that change in a little bit. But basically, you can write the equivalent torch run command using accelerate launch by just specifying multi-GPU. So I say torch run, right? Number nodes 1, num procs 2, script.py. And I can do accelerate launch multi GPU. It should say num processes equals 2 and script.py. And what the num processes lets us have instead of this nproc per node, so pretend that's num processes, is torch run has their special thing, deep speed has their special thing, torch XLA, which runs on TPUs, has their special thing. Accelerate just will go, I know what this means, go run it on that. And then, of course, also, if you just want to go based on what your system has, accelerate config also lets you write a quick default. So you can just say accelerate config default and be on your way. Now let's talk about how this becomes important for fastai. So as we all know, if you use fastai, generally you like using Jupyter notebooks. And Jupyter notebooks typically only run off of a single GPU. Accelerate, and in turn Sylvan Guger, created a notebook launcher function. And essentially, what this will do, as it kind of sounds, is and you can launch various functions from your Jupyter notebook and utilize all of the GPUs that are available there. And so you don't have to switch to the CLI. You can keep the Jupyter interface if you're a fan of it and still be able to have access to everything. And I guess I don't talk about this here, but well, no, I should. Ignore that. I believe there's a later section that talks about what I'm thinking of. So now let's talk about a training library. So remember, accelerate launch will do the thing, run to be ready for multi GPU. And an important thing I'm going to mention here is this does not mean that you need to use accelerate to use accelerate launch, right? So you don't have to use this training library. It's completely separate. So this is not necessary for you to run, say, PyTorch code or say Transformers code along with accelerate code or fastai code. But how do we ensure that it's actually using all those GPUs if you're not specifically stating to? Like you're not using all these wrappers that all these libraries utilize. So, as I basically mentioned, just when it comes to the CLI, it's, a few extra parameters. When you get into the training code, it gets a lot worse. You have to worry about how multi GPU behaves using something called PyTorch distributed. And that is different for the data loaders, that's different for the model, and its model wrapper that it uses to bring your model onto the multi GPUs are different than TPUs. And so there's a lot of custom code if you were to write one script that can fully be ran on every device, right? CPU, GPU, TPU, and Mac as well. Accelerate solves this by basically saying, okay, I'm going to give you a few lines of code. We're going to change them. And we're going to handle all of this device placement nonsense and special behaviors and provide you an interface so that way it's still sane for you. What do I mean by this? So let's take, for example, this training loop, right? It's a simple PyTorch training loop that iterates over a batch, zeros the gradients, gets the outputs, calculates the loss, and so on and so forth. The changes post accelerate looks like the following. So we added an import statement here. And we had an import statement here, built this accelerator object, called this accelerator prepare function that has a few things. We no longer have to, oh, thanks, Querto. We no longer have to do the device placement ourselves. And instead of calling loss.backward, we call accelerator.backward. What this hints at is anytime the accelerator gets involved, there is some sort of weird behavior that occurs on these distributed systems. And so if so, we just need to use the accelerator object. That's what it's there for. So let's talk about what happened in that accelerator prepare, right? That was the first part right here, where we pass in the data loader, model, optimizer, and scheduler. Basically, everything that is a PyTorch class to some degree or touches PyTorch, essentially. So when we first created that accelerator object, it looked at the config of the environment and inside it as well. And then after it's all prepped for this configuration, this could be stating things like what mixed precision to use, how the data loader should be split up, for instance. The data loader will be transformed into what is called a sharded data loader with a D. And what will happen is each time you draw one batch of the data, it'll get split across all of the GPUs. And this can either happen with subsections of the data set being stored on every single GPU to keep RAM lower, or one CPU has all of the data, and then as it's pulled out, subsets of it are sent to the GPU. What's important here with this, however, is so say I have a batch size of 64, okay? And I run this on a single GPU, so it's seeing 64 images at one time. How Accelerate handles the data loader processing is it doesn't say, okay, if I'm using two GPUs, then I'm going to use a batch of 64 total. So it's going to be two batches of 32 images on each GPU. It's going to use a batch of 64 on two GPUs. And the basic idea behind this is to make it a bit more efficient for you to train and a bit easier to understand. Like, okay, it runs on one. Every single process is going to have a batch size of X, not, oh, what is X divided by 8? And that's what I need to run. The schedulers and whatnot, as I'll talk about in a moment, handle for this and account for it. So it's not something wild and random that we're trying to throw at people. So next, the model was wrapped. And so I hinted at this also a little bit earlier. And basically what this means is, so Torch Distributed and Torch XLA have their own model wrappers. Because when you, say, are training on multi-GPU, each GPU needs to have a copy of the model. And there's two ways you could do that. The first way would be load in a single model and then, or a single model on each GPU, right? So that's a lot of instantiating of a GPU and going through that. Or You instantiate one model and then send that model, clones of it, to all the GPUs. Specifically, that means in the sense of there's only really one fabric of memory and they're passed around. And I might be going in circles now, but this is the difference between how Torch XLA does it and Torch Distributed. Distributed requires a copy of the model on every single GPU. So it's using a bit more CPU space because you have n models loaded in memory. Torch XLA actually lets you basically pass the model around as it's training. So as it's updating the gradients or getting outputs, they get passed one to another very, very quickly, almost instantaneously, and it makes it still very, very, very efficient while also not over enveloping your memory. Because with TPUs, for instance, you typically have like 8 nodes on there. So that's 8 processes that can train on. So you're gonna have 8 copies of a model in memory. That can get very big very quickly, which Torch Distributed has that problem. But it's sort of a pros and cons thing. And if you have access to a TPU, that's nice. TPUs are very powerful machinery that can help train even faster than GPUs in some cases. But it all is just what you have access to. That was a very long tangent. And then finally, we need to care about the optimizer and the scheduler. So these two were converted into what are called accelerated optimizers and accelerated schedulers. And their basic role is the optimizer knows when to step, what step function to call. That is why we got rid of the regular loss.step there. And instead, we pass that into the accelerator. Because in some cases, you still call, loss.backwards. But in other cases, you don't. TPUs have their own special function that they want you to use for doing the backward pass. I don't believe Torch XLA, or I don't believe Torch Distributed does, but say Deep Speed, that does. And so this way, we can handle, okay, I know what you want to call. We're going to do the backward pass based on what you have here. And then the scheduler is also there because given how I defined the data loader, right? We're sending n batches based on what you defined originally for the scheduler. Since we're essentially duplicating that process n times, right? If I have a scheduler that's set to step for 3 steps, I have 3 GPUs, and I have, say, 3 batches of 64, right? So normally on one GPU, you would train for 3 iterations and be done with it. What Accelerate does is, okay, I have 3 GPUs. Each batch is going to be done instantaneously of those 3. And the model weights will be updated in accordance based on the scheduler properly. And so what it will do is step the scheduler on each setup. So that way the full scheduler is seen and the optimizer is properly using the schedularized weight when updating. And so it's a nice way to train faster because you're just seeing more batches of data at once. But we need to make sure the scheduler and the optimizer get updated to allow for this essentially to happen. Now, I think like 6 months ago now ish, maybe 5 months ago. No, that would have been October, so that would have been 3. I worked with Jeremy on bringing Accelerate into FastAI to help handle all of this. That is also why it is featured in this course, because it relates to FastAI. So with FastAI now, you can still use that notebook launcher to train on FastAI in a distributed setup in a notebook. And on top of that, it also uses Accelerate for the distributed parts. Now, it requires a few steps. To change your code to use the notebook launcher, this is what I wasn't sure if we had to talk about a second ago. To use the notebook launcher with FastAI specifically, you need to migrate the data loader's creation inside of a training function that we're going to pass to this thing. And you need to use a new context manager called the distributed context. And with this already existed, but the existing implementation did not let you use the notebook launcher. So here's what I mean. This is a quick snippet from the distributed app examples. And we're going to use from fastai vision.all import star, right? Vision. You're going to import the distributed section of the library. And this is what will bring in all of the distributed parts that lets accelerate work in the back end of the learner. Now you can define things like getting data and whatnot in or outside of this training function. And remember, this is a notebook. So in its own cell, I can have path equals untar data. And then I need to define some training function I'm going to pass to the notebook launcher. This is where I'm going to create those data loaders. And then I'm going to pass the learner in. I'm going to create a learner. And then I'm going to use the with distributed context. Specify I'm going to be using this in a notebook. And this is if you get an error of something about thinking the batch normalization, set it to false. And I'm going to fine tune. So this is my entire training function from data loader creation to training, and then generally from here also exporting. And then finally, I can just say notebook launcher, train, not going to take any arguments. And I want you to train on 2 GPUs. Now, something important to note here is Accelerate can handle mixed precision for you. However, Jeremy has preferred that we use FastAI's mixed precision instead of Accelerate's. And so generally it's recommended when using Accelerate with FastAI to use the FastAI callback system as a priority rather than Accelerate. And a few more important notes on this. No code should touch the GPU before calling Notebook Launcher. The reason for this is how we're able to pull off this magic is essentially we spawn the CUDA process, right? When you first run .CUDA on anything, the torch will tell your GPUs, hey, I'm going to use you, I'm going to allocate a little bit of memory, and then we're going to go from there. Initiate a conversation between the two. That is what we call spawning. And no code should touch the GPU to spawn before using the notebook launcher. Because otherwise, what the CUDA drivers and what CUDA will essentially tell you is, hey, we already did this for this spawning method. You're wanting to do something else now, but I'm already initialized, essentially. You've already made me. You can't do that. And so you'll get this CUDA was already initialized, error, please restart the notebook. And basically what that means is somewhere you're spawning CUDA in a particular way, be it either an import or through calling .CUDA to something unintentionally. And as a result, you should put that inside the training function. So inside of this function here is everything that should touch CUDA. Now your next question is, well, wait, why is the data loader creation over here? Because I don't think I mentioned this yet. When you build data loaders in FastAI, FastAI will do essentially what's called a dummy check. And so when this data loader is created, well, actually, let's go with this. You remember how we had those setups, right? That setup that ran through the file or say images to extract all of the possible labels. That setups is essentially going through all of the transforms that we have and applying it to some data. Normalize also has a setups if you don't pass in statistics, and even then it still calls it. And normalize is a GPU transform, so that is where CUDA code comes in. So this is why this data loaders call needs to be in this training function, because this will actually initialize CUDA for you, even if you don't realize what's happening because you've never specified CUDA anywhere and it doesn't even look like it would go do something. And as I mentioned before, generally it's recommended on things that Accelerate can do to let fastai handle it. So Accelerate can handle things like gradient accumulation and then of course mixed precision. Um, as the framework gets more complex, generally just stick with the in-house callbacks if you're going to use fastai. If you're gonna, use PyTorch, absolutely go hog wild. This is just specifically for fastai. And then finally, make sure Notebook Launcher is the last thing to run after everything is complete. Just because, and I need to experiment with this, but I'm pretty sure you can't maintain the memory states in there just based on how it works. So act like the Notebook Launcher is kind of a end of code. And actually, that's the end of the fastai lesson. So basically, this is a TLDR of how to do fastai with Accelerate. For a full presentation on how to use Accelerate, if we actually go over to Hugging Face, and I will put a link to this. I almost did this as part of the presentation today, but I decided to do something different. I have a space called Accelerate Presentation. And as you notice, the title at least looks very similar. However, this is a much longer presentation that covers even more areas, such as the big model inference. And I highly recommend you go through this and take a peek at it. It covers a few more things in depth on what Accelerate can do. This was what I was expecting to show up, by the way, in this. It's just a little GIF showing all of the configs that you run through this little CLI interface. Let's go see. We have questions. I understand that notebooks are used a lot, but I don't think that'd be the best approach per se. That's just my personal take. I'm more anti notebook than notebook now, just because I've lived it. But I hear why that could be enticing. All right. With that, let's talk about training big models for a little bit. This is also going to piggyback off of Accelerate. I'm going to talk about this deep speed idea and what that is. You might have heard about it as something that allows you to train super huge models.